Good morning everyone. Today I will present the paper Detecting Hallucinations in Large Language Models Using Semantic Entropy, which is published in Nature in June 2024 by researcher at the University of Oxford. I will focus on the abstract, introduction and results, while my teammates will explain the methodology and code later. So, we know that models like ChatGPT or Gemini can sound very confident, but sometimes produce completely false answers, which is called hallucination. So these can have serious real-world effect like fabricated legal citation or unsafe medical advice. So the big question is how can we detect when a model answer is unreliable? So this type of hallucination in this paper introduce confabulations. So what is confabulations? So this paper focus on a specific kind of hallucination which is called confabulation. That means arbitrary incorrect answer that change with random seeds, which is not systematic error. Okay. So example, like suppose when we asked the LLM what is the target of Sototsi, the model sometimes say KRAS G12C, which is right, and other times it say KRAS G12D, which is wrong, even with the same prompt. So this is called confabulation in this paper. Okay. So what is the limitation of previous method? So earlier method tried two things. One is supervised training with labeled hallucinations or token based entropy, which is counting the how much the text vary. But unfortunately both are failed. Why? Because supervised system don't generalize the new task, and token entropy can't tell the difference between different word and different meaning. So the authors propose a meaning level approach to solve this. So what? So we need actually what? One method which will be unsupervised, which should be domain independent, and which will be meaning based, not a word based uncertainty estimator. So the key idea is called semantic entropy. What is this? The instead of measuring uncertainty over a word, it measures uncertainty over meaning. The model generates several answers and we group together the ones that mean the same things. Okay. So high entropy means high uncertainty and all possibly hallucinations. So go for the example. What is this actually? So when suppose here simple example, if the question is where is the Eiffel Tower, answers like Paris, it Paris, and France capital Paris, both three have same meaning. So we can keep as a same cluster. You can see one cluster is this one, means as all three have the same meaning. Similarly, Rome and Itzum, both two have same meaning, so we keep these two as cluster, and Berlin is also one cluster. So in this way, we are keeping total three cluster in this semantic entropy using. But if we use the naive entropy, then all six will be the different because they using the word base. You can see the word as different, so they can choose the different. So this is just one example of semantic entropy. Now, what is the experimental setup? The authors the authors tested this method on several datasets from general trivia and reading comprehension to biomedical and math questions using models like Llama 2, Falcon, Mistral, and GPT-4. Importantly, their approach is unsupervised. No label data or no model retraining needed. Now, this is the results the author published. The results are like uh, we can see they are introducing two metric actually, AUROC and AURAC. AUROC measures how well uncertainty predicts wrong answer, and AURAC measures how much accuracy improve if we reject high uncertainty cases. So across all dataset and models, semantic entropy and its discrete variant achieve the highest AURAC and AUROC. That means the best identify when the model is likely to be confabulate is the semantic entropy or discrete semantic entropy. So in this plot, they were showing several data set and then showing the best is the semantic entropy or the discrete version of the semantic entropy, and then showing paragraph level. What is this? Now for the long form GPT-4 biography, we see that discrete semantic entropy achieves both the highest AUROC and AURAC. So the rejection accuracy curve show that if we reject the top 20% most uncertain claims, the remaining answers accuracy rises from about 70% to 80%. That means the method can effectively identify the unreliable parts of a text. So that we need actually. So this is a big step forward factual trustworthy LLM outputs. Now, now the question is when semantic entropy helps. So it's a simple example that if we ask some question like when asked about industrial sector, the model gives different phrasing like industrial sector or heavy engineering. Both have the same meaning. So if you use semantic entropy, then detects consistency of meaning. So it is a low uncertainty. So, but while naive entropy wrongly flag it as uncertain. So sensitive to meaning, not just word choice. So what are implication and significance? So this so that large language models often know when they don't know. Semantic entropy makes that uncertainty measurable. It does not need retraining or label data and can be used to warn users or skip risky answers. So it's promising step towards safer and more trustworthy AI systems. Then go summary. To sum up, the paper tackles the problem of hallucinations by measuring uncertainty at the level of meaning. The proposed semantic entropy method generalizes well, works across models and tasks, and improves reliability. Now I will hand over to my teammates who will explain how the methodology works in details and show the code. Thank you.
Hello everyone. So I will be explaining the methodology section of this paper. That is how the authors developed and implemented the concept of semantic entropy to detect the hallucinations or more precisely confabulations in large language models. Here is the outline of what I will cover. I will start with the overall objective, move into the background concepts like uncertainty estimation, then walk through the semantic entropy algorithm and which will include the prompting templates, baseline and how it was implemented. Now, the main goal of this method was to detect when a large language model output is likely to be arbitrary or ungrounded. That is what they called a confabulation. Instead of measuring uncertainty over the words, they proposed measuring uncertainty over the meanings. The key idea is something that they called semantic entropy. That is essentially how diverse the meanings of the multiple possible outputs are from a single prompt. It works with any LLM even when the model's probability outputs are not available. To detect confabulations in LLM, they used a principle that the model will be uncertain about the generations for which its output is going to be arbitrary. For the uncertainty estimation, they use the predictive entropy. Predictive entropy measures how uncertain a model is about its output. If the probabilities are spread out, the entropy is high, and if the model is confident, entropy is low. But for large language model, this doesn't work directly because multiple sentences can have the same meaning. For example, Paris and the capital of France is Paris are identical in meaning, but the token level entropy treats them as different. So this can be a challenge for the LLMs. Here is the core pipeline. Here in step 1, they generated multiple answers to the same question using different random seeds. In the step 2, they clustered the answers by semantic meaning using the entailment checks. And in the step 3, they computed the entropy over all these meaningful clusters. If the meanings are all similar, then the entropy is low. That is, the model is confident about this output. And if the meanings vary widely, then the entropy is high. That means that it signals a risk for confabulations. So first they sampled multiple generations from the same model for a given question. Each sample uses random seeds and temperature based sampling, like requires sampling at value 0.9 and top k sampling at a k value of 50. This gives a diverse set of plausible answers capturing the model's range of possible outputs. These answers will be later compared semantically. Then they clustered these answers by the semantic equivalence. Two answers belong to the same cluster if they entail each other, that is, if both imply the same thing. For example, Paris is France's capital entails that the capital of France is Paris because they mean the same thing. They check the entailment using models like Debata A large MNLI or prompting GPT 3.5 and GPT 4 to decide between the entailment, contradiction, or neutral. This gives the equivalence classes representing the distinct meanings. So they build up these classes of semantically equivalent sentences by checking if new sentences share a meaning with any sentence that they have already clustered and then adding them to the cluster. So after clustering, they computed the probability for each meaning cluster, summing the probabilities of all the sentences in the cluster. Then they computed the semantic entropy over these clusters. They estimated the likelihood that a sequence generated by the LLM belonging to a given class by computing the sum of probabilities of all the possible sequence of tokens which can be considered to express the same meaning. If most of the probability mass lie in one cluster, then the entropy is low, meaning that it has a consistent confidence. But if it is spread out across many clusters, then the entropy is high. That means the model is uncertain or making things up. Next, for the scenarios in which the sequence probabilities are not available, they proposed a variant of semantic entropy which they call discrete semantic entropy. Discrete semantic entropy approximates the probability of the class semantic class directly from the number of generations in each cluster while disregarding the token probabilities. Here they approximated the probability using this formula where ni divided by m is the proportion of all the sampled answers which belongs to that cluster. So here is a worked example where is Eiffel Tower and the model answers Paris is Paris, France capital Paris. Since three things mean the same thing, so they are clustered into a cluster class 1, and Rome and Berlin they mean different things, so they are clustered in different clusters. And then they computed the symmetric entropy of these clusters. They tested their method on several models like Llama 2, Falcon, Mistral, and GPT-4 across datasets like Squad, Bio, ASQ, and Trivia QA. For each question, they generated 10 samples and computed the symmetric entropy. The metrics they used were AU-ROC and AU-RAC. AU-ROC measures the reliability of a classifier accounting for both precision and recall. The AU-ROC can be interpreted as the probability that a randomly chosen correct answer has been assigned a higher confidence score than a randomly chosen incorrect answer. For a perfect classifier, this is 1. And the next is AU-ROC, that is the total area enclosed by the accuracies at all the cutoff percentages. For the baselines, they used to compare their semantic entropy was first the naive entropy, which is a token base and it tends to overestimate the uncertainty. The next is the embedding regression model, which is a supervised approach using logistic regression on the hidden states. It is a supervised baseline. In the paper of the embedding regression model, the authors fine-tuned their LLM on a dataset of questions to predict whether the models would have been correct. So rather than fine-tuning the entire LLM, what they did, they simply took the final hidden units and trained a logistic regression classifier to make the same prediction. And the last one is the probability of true model. Here the model first sampled m answers and then it was prompted with the list of all answers generated, followed by the highest probability answer and a question where the answer is true or false. To boost up the performance, they also perform few shot prompting where they give up to 20 examples from the training set which are randomly chosen. The advantage of semantic entropy is that it was unsupervised, so it didn't require any training data, and it also works for unseen tasks or domains. This is a pseudocode part. The code will be explained by my teammate in the next part of this video. So for the computation of the entailment, they use the prompt something like this, that we are evaluating answers to the questions. They gave two answers and they ask the question if answer 1 semantically entail answer 2, and the model had to respond with entailment, contradiction or neutral answer. And for the sentence length generation, they use the template like answer the following question in a single brief but complete sentence, and then they gave the question. Here are some of the purposes, like keeping the answers concise, making it easier to compare the semantic meanings across multiple generations, and avoiding long uncertain responses that can distort the entropy. So coming to the summary of the methodology, to summarize, semantic entropy quantifies the uncertainty in meaning, not wording. The process consists of three steps, that is generating multiple answers, clustering by the meaning, and computing entropy over those clusters. It is simple, unsupervised and effective even for closed source models like GPT-4. This method actually accurately flags when the LLMs might be making things up. This code discussion and walkthrough will be demonstrated by another teammate. Thank you. Hello everyone. So now I will be presenting the code. So here we imported all the required libraries. We also imported the helper modules for the OpenAI and Hugging Face model handling. Finally, we set the device to GPU if available, and otherwise it is CPU. Now, this is a simple base class for all the entailment models. It defines a placeholder method, that is safe prediction cache, that subclasses will override later. This ensures a consistent interface across different entailment models. Now this class loads a Microsoft Debugger V2 X large MNLI model from Hugging Face. It is a natural language inference model. It can tell if one sentence entails, contradicts or is neutral with another. We move it to the appropriate device for faster computation. Now this check implication method takes two takes, for example, two possible answers. It runs through the debugger model and gets logics for these three classes: contradiction, neutral and entailment. The class with the highest probability is our predicted relationship between the two sentences. The numerical label, that is 0, 1 or 2, will later help us decide if the two model outputs means the same thing or not. This class provides a generic way to perform entailment checking using large language models like GPT or Llama. It also supports caching results to avoid recomputing the entailment judgments for the same sentence pairs. In this constructor, we initialize a cache of previous entailment results. The cache can be loaded from a WNB run ID or created empty. If entailment cache only is true, then the model won't make new predictions, it will only use the cache. This check implication function is the main method here. It builds a natural language prompt asking the model whether text 1 entails text 2. Each prompt is hash, so we can check if we have computed this before. If the result is already cached, we reuse it. Otherwise, we call the model to predict whether the relationship is entailment, neutral or contradiction. Based on the model's text output, we map it to a numerical label: 2 for entailment, 1 for neutral and 0 for contradiction. If the output is unclear, we default to neutral. Here is the prompt that we are sending to the model, and these are some lightweight wrappers around entailment LLM specifying which model to use. This function context entails response. It checks how well the context entails is generated response. It collects the entailment scores for all the responses and averages them. The output gives a measure of how consistent the responses are with the original context. Now this function gets semantic IDs. It groups multiple responses that are semantically equivalent, meaning they convey the same meaning even if they are worded differently. Now once we have the semantic cluster, we combine the probabilities of all the responses that belong to the same cluster. This is done in log space using the log sum exponential trick to maintain the numerical stability. Essentially, we sum the probabilities of all the semantic equivalent outputs. This predictive entropy and the predictive entropy row, these two functions compute the token level uncertainty from the model probabilities. This predicted entropy estimates the expected negative log likelihood, and the predictive entropy row function computes the entropy using the formula that is minus summation of p log p. They measure how uncertain the model is about the exact output that it produces. This function, that is the cluster assignment entropy, it measures the semantic uncertainty, that how spread the model's answers are across different meanings. If all the responses fall into one cluster, entropy is low, that is the model is confident. If the responses are evenly distributed among many clusters, then the entropy is high, that is the model is uncertain in its meaning. So to summarize, the model generates multiple outputs for a question, and then there is the entailment model which compares them pairwise. Then the semantic equivalent answers are grouped together, their probabilities are combined, and the entropy metrics are computed to quantify both syntactic and semantic uncertainty. This process gives a measure called semantic entropy, which captures how confident the model is, not just in the words but in meaning. Thank you.